On a day when Earth's winds carry autumn leaves and the familiar scent of changing seasons, a six-wheeled rover moves silently across the rust-colored plains of Mars. Perseverance rolls forward at the speed of a cautious beetle, its cameras sweeping across terrain that has known no footsteps for 4 billion years. The Martian morning arrives cold and thin, its salmon-pink sky holding barely enough atmosphere to stir the finest dust grains. Each wheel turn leaves temporary impressions in soil that will remain undisturbed until the next dust storm arrives to erase all evidence of passage. The rover approaches what mission scientists have labeled simply as Canyon Site Alpha, an unnamed depression carved into ancient bedrock where something unusual waits in the shadowed walls. Here, where the morning sun angles low across fractured stone, geological layers reveal themselves like pages in a book written by water and time. Each stratum tells of different epochs, different climates, different possibilities for a planet that once held rivers beneath a thicker sky. The canyon walls rise roughly 15 meters above the rover's position, their surfaces showing the familiar patterns of erosion and deposition that speak of flowing liquids and gradual accumulation. Perseverance extends its robotic arm with mechanical precision, positioning the Pixel instrument close to an outcrop that gleams with an unexpected color. Not the familiar iron red of Martian dust that has painted this world for billions of years, but something rarer, patches of deep blue-green that catch the pale sunlight like scattered gemstones embedded in stone. The spectroscopic analysis begins immediately. Invisible laser pulses reading the chemical signature of minerals that formed when this canyon knew the sound of running water. Each pulse lasts mere nanoseconds, yet reveals information about processes that unfolded across millennia. The rover's various instruments work in concert, like a symphony of scientific inquiry played out in the Martian silence. Mastercam Z captures high-resolution color images, while Supercam provides elemental analysis from a distance. The Rimfax ground-penetrating radar peers beneath the surface, mapping subsurface structures that might reveal the extent of these unusual formations. Each measurement adds another piece to a puzzle that began forming when Mars was young and water flowed freely across its surface. The initial data streams back to Earth across 140 million miles of space, a journey that takes between 4 and 24 minutes, depending on the orbital positions of both planets. The signals arrive at massive radio telescopes scattered across Earth's surface, then travel through fiber optic networks to the Jet Propulsion Laboratory, where teams of geologists and astrobiologists gather around monitors displaying wavelength graphs and elemental compositions. What they observe defies the typical Martian palette, challenging assumptions about the planet's chemical evolution and water history. These are hydrated sulfate minerals, copper-bearing formations that speak of groundwater seepage and chemical precipitation processes that require not just liquid water, but stable liquid water, present for thousands of years. The spectral signatures match those of minerals found in Earth's most arid regions, yet with subtle differences that hint at formation under conditions that existed nowhere else in the solar system. The copper content gives these formations their distinctive blue-green coloration, a hue that would have been invisible beneath the reddish dust that now blankets most of Mars. It only took 3 billion years for Mars to forget how to rain, though the planet still remembers in ways both obvious and subtle. The blue-green crystals embedded in the canyon wall represent a kind of planetary memory, each mineral grain a witness to humidity and flow, to underground rivers that move through porous rock carrying dissolved metals toward the surface. The rover's instruments detect magnesium, sulfur, and traces of copper elements that once danced together in ancient Martian springs before settling into these crystalline arrangements that now glimmer like forgotten jewelry. The precision required to detect these formations represents decades of technological advancement. Earlier, Mars missions might have passed by these deposits without recognition, lacking the sophisticated instruments needed to identify their unique chemical signatures. Only took 40 years of planetary exploration to develop eyes sensitive enough to see Mars as it truly was, rather than as it appears through the filter of accumulated dust and oxidation. The irony of discovery often lies in developing the right questions before the universe reveals its answers. There remains something mysterious about the precise formation mechanism, a puzzle that keeps planetary scientists returning to their data again and again. While Earth's desert regions produce similar evaporate minerals in dry lakes and salt flats, the Martian varieties show subtle differences in their internal structure, hints of environmental conditions that existed nowhere else in the solar system. Perhaps the lower gravity influenced crystal growth rates, allowing formations to develop in patterns impossible under Earth's stronger gravitational field. Or the different atmospheric composition affected how water molecules arrange themselves as they transitioned from liquid to solid preservation. The atmospheric pressure on ancient Mars remains one of geology's most debated topics. These mineral formations suggest pressures high enough to maintain liquid water at the surface. Yet other geological evidence points to a thin atmosphere even in Mars's early history. The copper-bearing sulfates might hold clues to resolving this paradox, their chemistry preserving information about the partial pressure of water vapor and carbon dioxide in the ancient Martian atmosphere. The canyon holds its secrets quietly, as it has for eons beyond human counting, its silence broken only by the occasional whisper of wind carrying dust across its rim. Perseverance photographs the formations from multiple angles, documenting their context within the broader geological setting. These images will be studied for decades, each pixel containing information about a world that once exhaled water vapor into morning mists, where underground aquifers sustained chemical reactions that Earth's geologists are only beginning to understand. The rover's memory banks fill with data that will outlive the mission itself, preserved for future generations of scientists who will bring new techniques and perspectives to these ancient mysteries. Only took 50 years of space exploration to realize that finding life on Mars might be less important than understanding how planets die. The blue stones wait patiently in their canyon wall, holding their chemical secrets with the same patience that stone has always shown, indifferent to the mechanical visitor that has come to read their story after so many ages of silence. They represent both an ending and a beginning, the end of Mars' active hydrological cycle, and the beginning of human understanding of planetary evolution on a scale that dwarfs all earthly experience. The canyon stretches before Perseverance like a wound in the planet's memory, its walls carved by waters that flowed when the solar system was half its current age. Ancient riverbeds snake through the depression, their meandering patterns still visible despite billions of years of wind erosion and dust accumulation. These channels follow the gravitational logic that all water obeys, seeking the lowest path through resistant bedrock with the patient persistence that only geological time allows. The rover's ground-penetrating radar reveals subsurface structures that extend far beyond what visible light can detect. Buried channels run parallel to the surface expressions, suggesting that this canyon system once supported both surface streams and underground aquifers. The radar signatures show distinct layers of sedimentary rock interspersed with what appear to be paleo-channel deposits, ancient river gravels now cemented into stone. Each layer represents a different phase in Mars's hydrological evolution, from vigorous flowing streams to intermittent seasonal flows to the final desiccation that left only mineral traces. Mastcam Z captures the subtle color variations in the canyon walls, revealing stratification that speaks of cyclical deposition over enormous spans of time. Dark layers alternate with lighter ones, suggesting periods of different water chemistry or seasonal variations in sediment load. The camera's filters can distinguish between iron oxides, sulfate minerals, and clay deposits, each representing different environmental conditions during the canyon's active period. Some layers show the characteristic red coloration of oxidized iron, while others maintain the gray-green hues of minerals that formed in reducing environments where oxygen was scarce. The mathematical precision of water's erosional patterns remains constant across planetary boundaries. On Earth, meandering rivers follow predictable curves determined by flow velocity, sediment load, and channel width relationships that geomorphologists have quantified through decades of fieldwork. The Martian channels display these same geometric relationships, their sinuosity ratios and wavelength to width ratios falling within ranges typical of terrestrial rivers. Only took 1 billion years for Mars to demonstrate that fluid dynamics operates the same way regardless of atmospheric pressure or gravitational field strength. Mission scientists compare the canyon's dimensions to similar features on Earth, finding striking parallels with rivers in the southwestern United States. The channel width suggests discharge rates comparable to the Colorado River during moderate flood stages, implying substantial water volumes moving through this system during Mars' active period. Yet the preservation of fine-scale features indicates that these flows occurred episodically rather than continuously, with long periods of quiescence allowing delicate mineral formations to develop undisturbed. The irony of studying ancient Martian rivers lies in their superior preservation compared to Earth's geological record. Terrestrial rivers constantly modify their channels, erasing evidence of earlier flow patterns through ongoing erosion and deposition. Mars's channels remain frozen in time, their last configuration preserved like a photograph of the planet's final hydrological breath. Only took the death of an entire planetary water cycle to create the perfect museum of fluvial processes. Spectroscopic analysis of the channel floors reveals mineral assemblages that require prolonged contact with flowing water. Phyllosilicate clays line some sections, their crystal structures indicating formation through chemical weathering of volcanic rocks under alkaline conditions. These clays could only have formed through sustained water-rock interaction over timescales measured in thousands of years. The presence of smectite minerals suggests fluctuating wet-dry cycles, as these clays form preferentially during alternating periods of saturation and desiccation. The rover's ChemCam instrument detects elevated concentrations of sulfur and chlorine in certain channel deposits, signatures of evaporative concentration as water volumes decreased. These chemical gradients tell the story of a dying river system, where diminishing flows became increasingly saline as dissolved mineral concentrated in shrinking pools. The final stages of channel activity appear to have involved hypersaline brines that deposited unusual sulfate minerals as they evaporated to dryness. There remains uncertainty about the climate mechanisms that sustained liquid water on early Mars. Global climate models struggle to maintain surface temperatures above freezing under the faint young sun that illuminated the early solar system. Yet the geological evidence for flowing water appears unambiguous, creating one of planetary science's most persistent puzzles. Perhaps greenhouse gases provided additional warming, or maybe the water flows occurred during brief periods of volcanic heating that temporarily thawed frozen ground. The preservation of organic carbon in similar geological settings on Earth raises intriguing possibilities for these Martian deposits. River systems concentrate organic matter through transport and burial processes, creating environments where biosignatures might survive for billions of years. The chemical conditions recorded in these channel deposits suggest pH levels and salinity ranges that could have supported microbial life, though detecting such ancient biosignatures remains beyond current instrumental capabilities. Perseverance documents each channel feature with methodical precision, building a comprehensive archive of Martian fluvial morphology. The rover's navigation cameras capture stereoscopic images that allow Earth-based researchers to construct detailed three-dimensional models of channel cross-sections and flow patterns. These digital reconstructions will enable future studies of Martian hydraulics using computational fluid dynamics models that can simulate ancient flow conditions. Only took 4 billion years for running water to become the most alien feature on Mars. The silence that now fills these channels carries no echo of the sounds that once reverberated through them: the splash of water over stone, the rumble of sediment transport during flood stages, the gentle murmur of base flow during dry seasons. The acoustic environment of flowing rivers has vanished from Mars so completely that even the memory of those sounds exists only in stone. The canyon walls rise on either side of Perseverance like the ribs of some vast fossil organism, their exposed layers chronicling the planet's transition from a world where water carved stone to one where only wind shapes the surface. Each stratum represents a chapter in Mars' environmental history, written in the language of minerals and preserved in the patient archive of sedimentary rock. The rover moves through this geological library like a reader turning pages, deciphering the story of water's gradual retreat from a planet that once knew the luxury of abundant surface liquids. The blue-green formations embedded in the canyon wall reveal their secrets slowly, one laser pulse at a time. Perseverance's SuperCam instrument fires focused beams of coherent light at the crystalline deposits, each pulse vaporizing microscopic amounts of material that emit characteristic wavelengths as they cool. The resulting plasma spectra appear on monitors at the Jet Propulsion Laboratory as peaks and valleys that correspond to specific elements: copper, sulfur, magnesium, and water molecules bound within crystal lattices that formed when Mars still possessed a substantial atmosphere. These hydrated sulfate minerals represent some of the most complex chemical formations yet discovered on Mars. Unlike the simple ion oxides that give the planet its characteristic red coloration, these compounds required specific conditions of temperature, pressure, and chemical activity to form. The copper content suggests interaction with hydrothermal systems, underground networks of heated groundwater that carried dissolved metals through porous rock before depositing them in surface expressions. Each crystal preserves a record of the water chemistry that created it, like a molecular diary written in stone. The spectroscopic signatures match closely with minerals found in Earth's Atacama Desert, where copper sulfate deposits form through groundwater evaporation in one of the planet's most arid regions. Yet, the Martian formations show subtle differences in their hydration states and crystal structures, variations that speak to formation under atmospheric conditions that no longer exist anywhere in the solar system. The lower atmospheric pressure on ancient Mars would have affected the stability of different hydration phases, creating mineral assemblages that serve as proxies for paleo-environmental conditions. Pixel's X-ray imaging reveals the internal architecture of these formations with unprecedented detail. Individual crystals show concentric growth patterns reminiscent of tree rings, each layer recording changing chemical conditions as groundwater composition evolved over time. Some crystals display evidence of dissolution and reprecipitation, suggesting cyclical wet-dry periods that allowed mineral structures to develop, partially dissolve, then reform under slightly different conditions. This cyclical pattern implies seasonal or longer-term climate variations that affected groundwater chemistry. The precision required to analyze these microscopic features represents a technological achievement that would have seemed impossible during the early decades of space exploration. PXL can map elemental distributions at the scale of individual crystal faces, revealing chemical gradients and compositional zonation that provide insights into formation mechanisms. Only took 50 years of planetary exploration to develop instruments sensitive enough to perform laboratory quality analysis on rocks separated by interplanetary distances. Mission geologists compare the mineral assemblages to similar formations in terrestrial environments, seeking analogues that might illuminate the conditions under which the Martian deposits formed. The closest Earth parallels occur in geothermal areas where underground hot springs deposit sulfate minerals as they reach the surface and cool. These environments support diverse microbial communities that use the chemical energy of dissolved minerals to power their metabolism, raising intriguing questions about the biological potential of ancient Martian groundwater systems. The water content preserved within these crystal structures provides direct evidence for the availability of liquid water during their formation. Hydrated minerals act as time capsules, trapping water molecules within their atomic frameworks, where they remain stable for billions of years. Spectroscopic analysis can determine not only the presence of water, but also its isotopic composition, which carries information about the source of the water and the environmental conditions under which it was incorporated into the crystal lattice. There remains uncertainty about the duration of water activity required to form such complex mineral assemblages. Laboratory experiments suggest that similar formations require hundreds to thousands of years of sustained water-rock interaction, implying that Mars maintained stable hydrological conditions for extended periods during its early history. This contradicts some atmospheric models that suggest only brief episodes of surface water activity, creating an ongoing debate about the nature and longevity of Mars's ancient climate. The irony of these discoveries lies in their preservation through planetary death. The same processes that ended Mars's active hydrological cycle also created the conditions necessary to preserve these mineral formations for billions of years. The loss of atmospheric water vapor eliminated the chemical weathering processes that would have gradually destroyed these delicate structures, while the cessation of tectonic activity prevented their burial or metamorphic alteration. Only took the complete desiccation of a planet to create perfect preservation conditions for its hydrological history. Perseverance's drill system prepares to extract samples from these formations, a process that requires extraordinary precision to avoid contamination while preserving the delicate crystal structures. The drill bits rotate at carefully controlled speeds to minimize heating that might alter the mineral phases, while pressurized gas flows remove cuttings without introducing terrestrial contamination. Each sample represents a potential time machine, carrying molecular-scale information about Mars's environmental conditions billions of years into the future. The sampling process itself becomes a meditation on the scales of time and space that govern planetary evolution. The rover operates with mechanical patience, each movement calculated to maximize scientific return while preserving irreplaceable geological specimens. The drill extends slowly into formations that took millennia to develop, extracting material that will be studied for decades using analytical techniques that have not yet been invented. Trace element analysis reveals the presence of rare earth elements and heavy metals that could only have been concentrated through hydrothermal processes. These chemical signatures suggest that the groundwater systems responsible for these formations were connected to deep crustal sources, perhaps associated with the volcanic activity that characterized early Mars. The metal concentrations provide constraints on the temperature and pH of the ancient groundwater, parameters that help define the habitability potential of these environments. Only took 1 billion years for chemistry to become archaeology on Mars. The blue-green crystals maintain their molecular structures with crystalline patience, indifferent to the passage of geological epochs that transformed their planet from a world of flowing water to a monument of mineral preservation. They represent both memory and prophecy memory of conditions that once existed, and prophecy of discoveries yet to come, as human understanding of planetary geochemistry continues to evolve through the patient examination of stones that traveled across space and time to reveal their secrets. The chemistry of evaporation operates according to principles that transcend planetary boundaries, yet each world adds its own signature to the process. As ancient Martian groundwater emerged at the surface through springs and seeps, it carried a dissolved cargo of metals and salts accumulated during its journey through subsurface rock formations. The lower atmospheric pressure on early Mars meant that water boiled at temperatures far below Earth's standard, creating unique conditions for mineral precipitation that left chemical fingerprints unlike anything found in terrestrial environments. Perseverance's instruments detect the layered architecture of these evaporate sequences, each stratum representing a different stage in the concentration process. The bottommost layers contain minerals that precipitate first from dilute solutions, primarily gypsum and other simple sulfates that require minimal evaporation to reach saturation. Higher in the sequence, more exotic compounds appear polyhydrated sulfates that form only under specific temperature and humidity conditions. Their crystal structures, preserving information about the atmospheric water vapor content during their formation. The copper-bearing minerals that give these formations their distinctive blue-green coloration represent the final stages of the evaporation process. Copper sulfates possess high solubility compared to other metal compounds, remaining dissolved in groundwater long after iron, calcium, and magnesium have precipitated out as separate mineral phases. Only when evaporation concentrated the remaining brines to extraordinary levels did the copper finally crystallize, creating the sapphire-hued deposits that now catch the pale Martian sunlight like fragments of a vanished ocean. Spectroscopic analysis reveals the presence of hydrated phases that contain multiple water molecules within their crystal structures. These minerals formed under conditions where atmospheric humidity provided a constant source of water vapor to balance the ongoing evaporation process. The delicate equilibrium between water loss and water gain created an environment where complex hydrated compounds could achieve stability, their formation requiring precise atmospheric conditions that existed briefly in Mars's geological history. The mathematical relationships governing evaporative mineral sequences remain constant across planetary environments, yet the specific compounds that form depend entirely on the chemistry of the parent water and the physical conditions during precipitation. On Earth, similar evaporation sequences in closed basins produce predictable mineral assemblages that geochemists can use to reconstruct ancient lake chemistry. The Martian sequences follow the same thermodynamic principles, but yield mineral combinations that reflect the unique composition of Martian groundwater and the planet's distinctive atmospheric evolution. Mission scientists calculate the water volumes required to produce the observed mineral deposits, arriving at estimates that suggest substantial groundwater reservoirs beneath the ancient Martian surface. The mass balance equations indicate that each square meter of mineral deposits represents the evaporation of water columns several meters deep, implying either very long-duration seepage from modest springs or shorter-duration discharge from more vigorous groundwater systems. Only took a planetary water cycle to create chemistry sets that would puzzle geologists billions of years later. The preservation of delicate hydrated phases presents a paradox that challenges current understanding of Mars's atmospheric evolution. These water-bearing minerals should have gradually dehydrated as Mars lost its atmosphere and surface pressures dropped below the stability fields for hydrated compounds. Yet, many crystals retain their water content, suggesting either more recent formation than previously thought or exceptional preservation conditions that prevented dehydration over geological timescales. Laboratory experiments attempting to replicate Martian evaporation conditions face fundamental challenges related to the planet's unique atmospheric composition and pressure regime. Terrestrial vacuum chambers can simulate the low-pressure environment, but reproducing the precise gas composition and trace constituent concentrations of ancient Mars requires sophisticated experimental setups. These studies suggest that the Martian evaporation process occurred under conditions that have no exact analog in Earth's current environment. The irony of studying these ancient chemical processes lies in their revelation through instruments that themselves depend on precise chemical analysis. SuperCam's laser-induced breakdown spectroscopy operates by creating miniature plasma events that reach temperatures of tens of thousands of degrees, temporarily recreating stellar conditions to analyze minerals that formed through gentle evaporation under a dim young sun. Only took 4 billion years of planetary evolution to develop technology capable of reading the chemical signatures of its own deep past. Trace element distributions within individual crystal faces reveal episodic changes in groundwater chemistry that suggest multiple sources contributing to the surface discharge. Some layers show elevated concentrations of elements typical of volcanic groundwater, while others display signatures consistent with deeper crustal sources. This chemical variability implies a complex subsurface hydrology where different groundwater flow paths converged at surface discharge points, creating opportunities for diverse geochemical processes. The stable isotope signatures preserved within these formations provide additional constraints on the temperature and source of the ancient groundwater. Oxygen isotope ratios reflect the temperature of mineral formation, while sulfur isotopes carry information about the source rocks through which the groundwater flowed. These isotopic fingerprints suggest formation temperatures consistent with modest geothermal heating rather than the extreme temperatures associated with active volcanism. Perseverance's analytical suite documents the spatial distribution of different mineral phases within the evaporate sequence, revealing patterns that reflect the hydrodynamics of the ancient discharge environment. Minerals that crystallize rapidly from supersaturated solutions occur in different locations than those that form through slow precipitation from near equilibrium conditions. This spatial organization provides insights into flow velocities, residence times, and mixing processes that characterize the groundwater discharge. There remains uncertainty about the timescales over which these evaporation sequences developed. Some mineral textures suggest rapid precipitation during brief discharge events, while others show evidence of slow crystallization over extended periods. The coexistence of these different formation styles within the same outcrop implies complex temporal variations in groundwater discharge, possibly related to climate cycles or seasonal variations in subsurface hydrology. Only took the death of an atmosphere to preserve perfect examples of planetary geochemistry in action. The blue-green crystals maintain their chemical compositions with molecular precision, each atom locked in place by crystalline forces that have remained stable across eons of planetary change. They represent libraries of information about processes that operated when Mars was young, their chemical messages waiting patiently for readers equipped with the instruments and knowledge necessary to decode the stories written in their atomic arrangements. Across the vast expanses of Earth's most arid regions, similar mineral formations tell stories of water's patient retreat from landscapes that once knew abundance. In the Atacama Desert of Chile, copper sulfate deposits gleam with the same blue-green luminescence that Perseverance now documents on Mars. Their crystalline structures formed through processes that mirror those occurring on the red planet billions of years ago. These terrestrial analogues provide a reference framework for understanding the Martian discoveries. Yet each world's unique conditions create subtle variations that reveal the distinctive character of planetary evolution. The Atacama's evaporate sequences formed over timescales that span thousands of years, as groundwater moved through copper-rich ore deposits before reaching the surface through springs and seeps. The extreme aridity of this region preserves delicate mineral formations that would dissolve rapidly in more humid environments, creating natural laboratories where researchers can study evaporation processes under conditions approaching those of ancient Mars. The mineral assemblages include many of the same compounds detected by Perseverance, though in different proportions that reflect Earth's higher atmospheric pressure and distinct groundwater chemistry. Spectroscopic analysis of Atacama deposits reveals formation temperatures slightly higher than those indicated by the Martian minerals, a difference attributable to Earth's more substantial atmosphere and closer proximity to the Sun. The terrestrial formations also show evidence of seasonal variations in mineral precipitation, with different compounds crystallizing during wet and dry periods of the region's minimal precipitation cycle. These seasonal signatures provide insights into the potential for similar cyclical processes on ancient Mars, where orbital variations might have created periodic changes in surface conditions. The preservation potential of hydrated minerals varies significantly between Earth and Mars, with the red planet's thin atmosphere providing superior long-term stability for water-bearing compounds. Terrestrial evaporates experience constant chemical weathering due to atmospheric humidity and occasional precipitation events that dissolve and reprecipitate mineral phases. The Martian formations exist in a chemical stasis that has persisted for billions of years. Their molecular structures frozen in configurations that reflect the atmospheric conditions of their formation. Death Valley's salt flats offer another terrestrial analog for Martian evaporation processes. Though the mineral assemblages differ due to distinct source rock chemistry and hydrological settings, the playa lakes of this region concentrate dissolved salts through evaporation, creating zonation patterns where different minerals precipitate at different distances from water sources. These spatial distributions mirror the layered sequences observed in Martian evaporates, suggesting similar physical processes operating under different planetary conditions. Mission geologists construct detailed comparisons between terrestrial and Martian evaporate textures, seeking patterns that might reveal formation mechanisms not apparent from studying either environment in isolation. The crystal habits of Martian sulfates show distinctive features that reflect formation under low atmospheric pressure, with crystal faces and growth patterns that differ subtly from their terrestrial counterparts. Only took 1 billion years of separate planetary evolution to create mineral museums that preserve the distinctive signatures of each world's environmental history. The kinetics of mineral precipitation operate according to universal chemical principles, yet the specific pathways followed depend critically on environmental conditions such as temperature, pressure, and solution composition. Laboratory experiments designed to simulate Martian evaporation conditions reveal precipitation sequences that match the observed mineral assemblages, providing confidence in interpretations of the ancient environmental conditions. These controlled studies also identify intermediate phases that might have formed temporarily before dissolving or transforming into more stable compounds. Trace element chemistry provides additional insights into the similarities and differences between terrestrial and Martian evaporation processes. The Martian formations contain distinctive ratios of rare Earth elements that reflect the composition of ancient Martian crust, while terrestrial analogs show patterns typical of Earth's continental geology. These chemical fingerprints serve as planetary identification markers, allowing researchers to distinguish between indigenous Martian processes and potential terrestrial contamination in future return samples. The irony of using Earth's driest places to understand Mars's wettest period reflects the temporal scales over which planetary environments evolve. Earth's deserts represent temporary features that will disappear as continental drift and climate change reshape the planet's surface, while Mars's evaporate deposits preserve permanent records of hydrological processes that ended billions of years ago. Only took the complete desiccation of one planet to create the perfect preservation conditions for understanding water's role in planetary evolution. Microbiological studies of terrestrial evaporate environments reveal diverse communities of extremophile organisms that thrive in the high salinity conditions associated with mineral precipitation. These findings raise intriguing questions about the biological potential of ancient Martian groundwater systems, where similar chemical conditions might have supported microbial life during the planet's early history. The preservation of organic compounds in terrestrial evaporates suggests that Martian formations might retain biosignatures if life ever existed in these environments. Perseverance's documentation of the Martian evaporate sequences provides unprecedented detail about mineral textures and associations that would be impossible to study through telescopic observations or orbital remote sensing. The rover's ability to examine individual crystal faces and measure elemental distributions at microscopic scales reveals formation details that rival those obtainable through direct laboratory analysis of terrestrial samples. This level of analytical precision transforms Mars exploration from reconnaissance to detailed field geology. Seasonal variations in terrestrial evaporate formation suggest potential mechanisms for the cyclical mineral deposition observed in Martian sequences. Earth's desert regions experience subtle changes in groundwater chemistry related to seasonal temperature variations and occasional precipitation events. Similar processes on ancient Mars might have been driven by orbital cycles that periodically change the planet's climate, creating the layered mineral sequences now preserved in canyon walls. There remains uncertainty about the biological implications of the chemical similarities between terrestrial and Martian evaporate environments. While Earth's high salinity mineral deposits support specialized microbial communities, the environmental conditions on ancient Mars might have exceeded the tolerance limits of any potential life forms. The chemical signatures preserved in Martian evaporates provide constraints on ancient water activity and salinity levels that help define the habitability potential of these environments. Only took 4 billion years for two planets to create complementary libraries of evaporation chemistry. Earth's active processes continue to form new evaporate deposits while gradually destroying older ones, maintaining a dynamic record of current environmental conditions. Mars preserves its ancient formations with crystalline patience, offering permanent access to chemical information about processes that operated when the solar system was young and both planets possessed abundant surface water under skies that no longer exist.